Hey, welcome to what I hope is the first video you're watching in this new topic. Occasionally confusing to some students, confusing to me. The topic is interparticle forces. In the earlier unit on bonding and geometries, you talked about ionic bonding and covalent bonding. We want to cover a few more bases now because there are other ways that particles can interact and form. You could call it a bond. It's a weak bond for sure. Yeah. Let's look at this picture. Here's a outline map of some of the major interstate highways in and around the U.S. of A. And the key prefix is inter, meaning between states. Yeah. So if I want to go to Evanston to get some fireworks, I get on I-80. Or if I want to go to Vegas to blow some money, I go get on I-15. Just kidding, I don't do that. But anyways, the I of I-15 and I-80 stand for interstate, and so it's a road that goes between states. Rarely any traffic lights, those are nice. Speed limit's 80 going to St. George. That's nice. Anyways, be careful driving. But I'm saying, in a similar way, if I look at the forces within a molecule of HCl, that's the intraparticle force. But between two particles of HCl, that's inter. So what does it say here? Occur between atoms of the same molecule. How about intra? And then intermolecular forces occur between the molecules of different molecules in the sample. So what did I say? Inter. Yeah. Yes, got it right. All right. Another example. If you care. If you don't, fast forward. Take a nap. I'll wake you up in a second. Come on, Mr. Slide. Move up there a little bit. There we go. Helps if you talk to it. So often a bond, a covalent or ionic bond, is represented by a solid line, sharing electrons or a transfer of electrons. But the relatively weaker interparticle force is represented by a dashed line or dots in between. So I guess the black is the intra, and the blue is the intermolecular forces. Black and blue, I believe. Yeah. So the previous slide had HCl, but here's the H2 and here's the Cl2. They also have at least some measure, although they are weak in this case, some measure of interparticle forces. Here's a tricky question. Thinking back to the unit on bonding, ionic and covalent, which of these ranking ionic, covalent, and intermolecular forces? The answer is intermolecular forces are the weakest forces, but in terms of ranking ionic and covalent, somewhat debatable on occasion. Most chemists would say that the range of ionic bonds is oftentimes weaker. The range of ionic bond strength is less than the range of covalent bond strength. Not the range. Looking at the average ionic bond strength and the average covalent bond strength, which is a misnomer because there really is none. We usually say covalent bonding is slightly stronger than ionic bonding, and of course that depends what covalent bond you're talking about and what ionic bond you're talking about. But we say, imagine dissolving in water. If a covalent substance dissolves in water, it does not break up into ions. But if an ionic substance dissolves in water, it does break up into ions. That's why we say that usually covalent's a little bit stronger than ionic. I don't know if that makes any sense or not. The first type of interparticle force occurs between two dipoles, two geometrically lopsided, and thus likely electrostatically lopsided molecules, polar molecules, and that means we have a positive side of one attracting the negative side of the other. The negative are slightly negative and slightly positive, slightly negative and slightly positive, slightly negative, slightly positive, and they kind of, at least in a weak way, not very strongly, but they align themselves. They tend to align themselves if they have, ability to roam around in a liquid, or a gas even, align themselves kind of oppositely and attract that way. There are some substances that have stronger dipole-dipole forces. I guess the stronger the dipole moment in the sample, the stronger the dipole-dipole forces, like water. But water is kind of special because it has this special kind of dipole-dipole force called hydrogen bonding. If the molecule is lopsided because of the HO bond, then now hydrogen bonding is not the bond between hydrogen and oxygen, or even between two hydrogens. It is the weak interparticle force between two molecules that have a hydrogen on one, have a hydrogen and an oxygen. So the hydrogen of one is attracted to the oxygen, nitrogen, or fluorine of a neighboring molecule. That's kind of why one reason why ammonia and H3 dissolve so well in water. They're both pretty small, very polar molecules, and the hydrogen of one water is attracted to the lone pair on the nitrogen. That's slightly negative, slightly positive. All kinds of pictures. You can Google images and find all kinds of models folks have put together about what they think hydrogen bonding might look like. And it is a fairly strong force as far as interparticle forces go. I think it is the strongest. Let's go. Hydrogen bonding is the strongest. General dipole-dipole might be slightly weaker. There's a couple of other examples. Here's a cool molecule with H and N, O and F. So hydrogen on this one might be attracted to another oxygen on a neighboring molecule, not these two, but this one attracted to another oxygen or another fluorine on a neighboring molecule of this sample. Yeah, alright, good enough. Here's a couple of graphs representing the boiling temperatures. Oh yeah, one reason why we care about these interparticle forces is so that we can enumerate and predict and understand boiling temperatures, melting temperatures, tendency to evaporate, surface tension, capillary action, stuff like that. Specific heats. So as I go from H2O to H2S to H2SE to H2TE, or perhaps I should say, as I go from H2TE to H2SE to H2S, the tendency seems to be that the boiling temperature decreases, but then all of a sudden it jacks way back up. The reason being hydrogen bonding. H2O and HF are able to hydrogen bond with each other. So in a pure sample of billions of HF particles, there's hydrogen bonding, attracting, sticking together. And if these particles stick together with a lot of interparticle forces, that kind of, in a way, delays or postpones to a warmer temperature the boiling of these substances. Interesting. Here's another, probably a little bit more clear graph. No hydrogen bonding all the way across. No hydrogen, no hydrogen bonding, and the green line and the blue line tend down until they get into some hydrogen bonding with the hydrogen and the nitrogen, or I should say the hydrogen on one NH3 attracted to the nitrogen of a different NH3, just like we had with the water and the HF. So boiling temperatures increase, and melting temperatures increase, and surface tensions increase, and viscosity increases. The third interparticle force, ion dipole forces, where I have an ion attracted to a dipole. It's of course what allows water to dissolve so many salts, so many positive, negatively held, compounds. Water can't dissolve all salts, but most salts with reasonable lattice energies that are fairly easy to pull apart. The negative side of water surrounds the positive ion, or the positive side of water attracts the negative ion, like we have here, and it just makes water a good solvent for the dipole of water attracting the negative or positive anion or cation. Here's acetone, which is also polar. It's a dipole. So the negative side of acetone, the oxygen part, attracted to the positive lithium ion. So lithium ions, lithium salts, lithium chloride, for example, probably dissolve pretty well in acetone. The last and weakest of interparticle forces is called London Dispersion Forces, they act between all molecules. Doesn't matter what they are. But it is the weakest of the forces, and it's only noticeable when there are no other interparticle forces present. So importantly, in nonpolar molecules, and no ionic things either. We think it happens because of a one one accidental, momentary, coincidental negative forces another molecule next door to be the opposite. So if the electrons are accidentally over here for a brief nanosecond, that's negative, and someone nearby will be forced to be positive, and that forces that to be negative, and so it just kind of like a wave effect at a sporting event. Let's see. We're talking about, dispersion forces. So the longer the molecule, like this butane or pentane or hexane, the longer and skinnier, the more London dispersion forces. Sometimes they're just called dispersion forces. This one boils hotter, colder, colder, coldest. So the longer it is, the more massive it is, the hotter it boils. Same story here. These have the same molar mass, 72 and 72. These are kind of put together in a bent fashion. But here, this has fewer interparticle forces, fewer London dispersion forces specifically, because it's kind of balled up, and this is all stringy and long. They can fit together, and if they can fit together, they can interact with each other a little bit more and be more sticky. Also, the more massive the particle, so fluorine, chlorine, bromine, iodine, the more heavy the particle, like iodine's a heavy atom, the more interparticle forces. So you see the boiling temperature, melting goes increasing and boiling goes increasing, and indeed iodine's a solid, bromine's a liquid, but these two are gases because the London dispersion forces in fluorine and chlorine are small, and they're larger in bromine and larger even still in iodine. Same trend holds for noble gases if you want to look at those. Boiling temperatures, helium, neon, argon, they're very simple atoms. They're chemically unreactive, and they are not dipoles. There's no ions, there's no hydrogen bonding, so all we have in a sample of xenon and radon or krypton is dispersion forces, London dispersion forces. And the larger or heavier your atom is, the more dispersion forces you have, the hotter it boils, or the hotter it would melt if you have a solid sample. I think we already went through this one. I'll do it again though. Do you remember what the ranking is then for the strength of the interparticle forces? Oh yeah, hydrogen bonding is the strongest. Really dipole. I guess I didn't list ion dipole. Dipole in general is made perhaps a little bit weaker than hydrogen bonding, but some consider hydrogen bonding a type of dipole force. And the London dispersion forces, or just dispersion forces, are the weakest. Arrange these solids, liquids, and gas in the order of weakest to strongest interparticle forces. What do you think? I think solids have the strongest interparticle forces. Solids followed by liquids, and gases have the, did I say that right? Strongest, medium, weakest. There we go. Choice is A. What do we affect interparticle forces? Boiling point? Yep. Electronegativity? Not really. It's just a kind of a property of how of electron configuration and how strongly the atom can pull electrons towards itself. Melting point? Melting temperature? Yes. Surface tension? Yes. So how about, what? Did I erase A? What is that? Okay. So anyways, boiling point, melting point, surface tension, viscosity, even heat capacity, but not electronegativity. Oops, there's the answer. Which of these has the largest surface tension? This one here has hydrogen bonding with the OH group. The H here would be attracted to another oxygen on a neighboring alcohol molecule. This is just dispersion forces, just dispersion forces, just dispersion. There's not even any dipoles there to worry about. They're all just dispersion forces. Which of these would have the greatest surface tension, i.e. dispersion forces that contribute to surface tension? And the answer is the longest and skinniest one that has the most hydrogens that can fit the closest together. That's a tricky one. I wish my other professor had perhaps put that one in there. He did though. It's A. The double bonds introduce kink organic chemistry question. Good to think about, though. We see the compounds are gases at room temperature. Um, all are gases except for one. Which one's a liquid? Which one has more forces, interparticle forces? The answer is this one, because it's lopsided. I think I drew a picture. I think I did. It's lopsided geometrically and electrostatically. Oxygen is very electronegative. This is the delta negative. That's the delta positive side. And it would probably have some measure, I don't know about hydrogen bonding, but it certainly does have dipole forces. It has hydrogen and oxygen, but this hydrogen is not attached to an oxygen. But now it still would have some hydrogen bonding. This hydrogen could be attracted to a negative oxygen of a different neighboring um, molecule. And choose a series of the range melting point. So easiest to melt to hardest to melt. Looks like they're all dispersion forces. I don't see any dipoles there. So, alright. I'm going to have to go with, the heaviest molecule, chlorine, Cl2, 35.5, 71-ish grams per mole, is the largest dispersion forces. This one's a little bit lighter. This one's a little bit lighter. This one's the lightest. So I'm going to have to go B, just based on masses. Alright, well, I don't know what you think about that, guys, but thanks for checking in, and I'm going to see you in class soon. Yay! Go rest.